We easily solve the equation x squared minus 2xy equals 8. Subtract x squared from both sides, divide both sides by negative 2x. You get y equals x squared minus 8 divided by 2x. Then your derivative of y with respect to x is easily found by the quotient rule using the prime for the derivative with respect to x. We have x squared minus 8, the numerator, derivative of that times the denominator, minus the numerator times the derivative of the denominator, divided by the square of the denominator. I got so used to writing primes that I just wrote that one as a prime. I squared it correctly down here. Okay, and that's, again, easily calculated. Derivative of x squared being 2x, derivative of 2x being 2. We get this expression. I'm not going to read it to you. And then it simplifies down to this. And, of course, the square of our denominator, which was 2x, is 4x squared. Okay. Now, there's another way we could have taken the derivative of this, and it's pretty much 6 1/2 dozen of the other. Which one's simpler? We have x squared minus 8 over 2x. We treat that as a quotient of two functions, and as we see, we get a derivative without a whole lot of trouble. Of course, we have to be used to the quotient rule, but it applies pretty easily in this case. We could alternatively have distributed the division by 2x, multiplication by reciprocal of 2x, getting x over 2 minus, 8 over 2x is going to be 4 over x. So x squared minus 8 over 2x gives us x squared over 2x minus 8 over 2x, which is x over 2 minus 4 over x. The algebra is very simple. And we can write that as 1/2 x minus 4x to the negative 1, where we then have two power functions. So that our derivative, derivative of 1/2 x, that's x to the 1, its derivative is 1x to the 0, which is just 1. So the derivative of this term is just 1/2. The derivative of x to the negative 1 is negative 1x to the negative 2. So we're going to get a plus 4 because of the negative 1. Negative and a negative is going to give us a positive. And it's going to be x to the negative 2. So we could write that as 1/2 plus 4 over x squared. Now, is that the same as this? Well, it looks a little different, but it turns out that 2x squared over 4x squared is 1/2. 16 over 4x squared is 4 over x squared, and you can easily verify that. Now, both of these equations were easily solved for y. What if I'd have put another term into this first equation, like, let's say, a couple terms like 4xy cubed plus 3y squared over x? Okay, well, we would have had y cubed in this equation, and then it would have been pretty much way too difficult to solve that equation. And sometimes you can put terms into the equation that just make it unsolvable if you're trying to solve for y. So you can't always solve your equation for y and take the derivative. And what we're going to lead up to is something we can do when that isn't the case. So we motivate first by looking at a couple of cases where we can solve for y. Then we're going to look at a couple of other equations, this being one of them. No, I take it back. This one is easily solved for y as well. And actually I need to talk about that. So if we look at this equation, it's another equation that can be easily solved for y. And we get y equals square root of x minus 3 over 3x squared. We can take its derivative using the quotient rule once more. And there's no there's no simplification of this that's going to help us. We could divide the 2x into the x squared and into the 8, but we can't do that with the x minus 3 under the square root. There's no good way to simplify this. We simply have to use the quotient rule, and it's going to work out. So again, we have now 3 examples of equations where we can solve for y, but there are many examples, and you'll see a couple of them shortly, where either it's way too much trouble to solve for y, or it's impossible to even attempt to solve for y.